All right, so question 11. Question 11 is just a right dimensional analysis question. We're told for question 11, right, we ran the 200-meter dash. So this is practice exam number 11. 200-meter dash in 19.3 seconds, right? How fast is that in miles per hour? So I would just convert this into meters per second, right? We did 200 meters in 19.3 seconds. So dividing that through, we got 200 divided by 19.3 seconds. So he was basically traveling about 10.36 meters per second. And now we just have to convert that to miles per hour, right? So I know for every 1 mile, I need 1,609 meters. So meters cancel out. We divide by 1,609 to get about 6.44 times 10 to the minus 3 miles per second. From there, we just need to go turn seconds into hours. And so we know, right, there are 3,600 seconds in 1 hour. So we multiply, seconds cancel out, right? Multiply by 3,600. And he was moving approximately 23.2 miles per hour. Right, so it's just dimensional analysis, looking at the units we have. We've got meters, we've got seconds. We want to convert that to units of miles per hour. So meters need to go to miles, and then seconds need to go to hours. All right, question 12 would be next, right? So question 12, I'll just answer that on the same page here. We know we've got this gold nugget, right, that weighs 201 troy ounces. And we want to basically find out right, the mass in grams. So no, the cost doesn't factor into the dimensional analysis because we don't use the cost anywhere. Right, so we want to find the mass in grams. Right, and so given the conversions that we have, we know that 1 pound equals 14.583 troy ounces. We're also told, right, that there's 454 grams in 1 pound. So that means we can go from troy ounces to pounds, because for every 1 pound, I'm going to have 14.583 troy ounces. So that cancels out, right? We divide 201 by 14.583, and that gives us 13.78 pounds. Right, but that's good to know that just like throwing in a random number makes the calculation a little bit harder. I should do more of that, of just throwing in some random numbers into some problems just to see what happens. Once we're in pounds, we can go from pounds to grams, because we know for every 1 pound, 454 grams. So pounds cancel out, we multiply by 454, and I get 6.26 times 10 to the 3 grams. 3 significant figures, because 201 troy ounces is 3 significant figures. Question 13 is next, right? So based on this newly discovered elements, got 4 known isotopes, right? So all we have to do for question 13 right is basically tabulate how many of each that we have. And so let's see, I've got 5 by 5, so there's 25 total. And of those 25, so we'll just start with, we've got A, we've got B, we've got C, we've got D. So A is 1, 2, 3, 4, 5, 6. So 6 out of 25. B is also 6 out of 25. C is 1, 2, 3, 4, 5, 6, 7, 8, 9 out of 25. So if you're looking at question 13 right now, I'm just counting how many of each isotope we have in the whole sample to find a percentage, right? And then the last one would be D, and I've got 4 D out of 25. And so just making sure that the math adds up, right? That's 10, that's 16. Yeah, that'd be 25. So I'm going to turn those into percentages, right? So 6 out of 25 is, yeah, 0.24, 0.24, 0.36, and then obviously 0.16. So that is the abundance, right, of those. Do you use the mass percent or the abundance formula? So this is not a mass percent question, right? We're using, you don't have to use the abundance formula. I think it's easier how we have it set up. No, if you had to convert from Celsius to Fahrenheit, I would give you the equation. So this is the percent abundance as a decimal, and now we're going to multiply it by AMU. So that way it's 29.12 AMU. This is 30.016 AMU. This is 31.024 AMU. And then this is 32.213 AMU. We're going to multiply all those together, add them up, and then that's our answer, right? So 0.24 times 29.012, I get 6.962. 0.24 times 30.016, I get 7.2038. 31.024 times 0.36, and I get 11.1686. And then 0.16 times 32.213, I get 5.154. Add those all together, so 11.1686 plus 7.2038 plus 6.9628, and I get something like 30.489. For our significant figures, right, I would say it should be 1, 2, 3, should be 3 decimal places. Yeah, 3 decimal places, because we counted to determine the percentage. So that's kind of an exact, I think of that as an exact number. So I have, yeah, I've got 5 sig figs there, which is 4 decimal places, 4 decimal places, right? 1, 2, 3, 4, 5 becomes 3 decimal places there. So we should only have 3 decimal places in the final answer. So 30.489. So in scientific notation, 3.0489 e to the 1 AMU, because we should have 5 significant figures in all of these, and that means 3 decimal places in that one. The rest of these would have 4 decimal places, but because we're limited by decimal places, it's a weighted average, right? It's not a pure add and divide by 4 average, because not everything is there in the same amount. So we're doing a weighted average based on 24% of the sample is this isotope, 24% is this, 36% is this, 16% is this. So that's why we don't just add and divide by 4. I think someone tossed in question 15 while I was working. Oh, question 15 be the last from this series, and then I'll jump to the next series. Right, a little bit of a dated question, but when I wrote the question a few years ago, I was pretty happy with it. But yeah, I probably should update it. Right, so practice exam question 15, right? Got a 15 karat diamond, and I want to know how many carbon atoms. So someone earlier in the chat asked if we could practice like going to atoms. I forget who asked, but this is a question where we're going to go to atoms for question 15. So you want to go from a carat of a diamond, right, to carbon atoms. And there's a few things we know, right? We know that 1 carat equals 200 milligrams. We know that carbon is 12.01 AMU. Right, so we got 15 carats. I know for every 1 carat, right, we've got 200 milligrams. So I think we've got like 3,000 milligrams. Is that diamond, right? That's step 1. Step 2, milligrams to grams, because our molar mass of carbon, right, is 12 AMU or 12 grams per mole. So I need to go from milligrams to grams. So I've got 3,000 milligrams, and I know there's 1,000 milligrams in 1 gram. So that diamond weighs 3 grams. Now we can convert that into now that we can convert that into 3 grams, we've got to find moles, right? So I know for every 1 mole, the molar mass tells me 12.01 grams. So 3 divided by 12.01. And we get about a quarter, right? About 0.2497 moles of carbon, right? So for the person that was asking how we go, right, to get atoms, in this case, we're going to go to atoms directly using Avogadro's number, because diamond is pure carbon. It's just 1 element. And we're going to do that using Avogadro's number, right? So for every 1 mole, I've got 6.02 times 10 to the 23 atoms of carbon. So we're going to multiply by Avogadro's number, 6.02 times 10 to the 23. And I get something like 1.5 times 10 to the 23 carbon atoms. 2 significant figures, because 15 as written, 15 carats as written was 2 significant figures. So I'll stop the video there.